as I didn't record any of that. One of the things that I want you to do within the course is to look for patterns and draw conclusions. Those conclusions do not have to be factually correct conclusions, but your explanation for why you're drawing those conclusions is kind of important. Okay? And in my mind is more important than being factually correct. Okay? Because if it is purely factually correct, you don't need me. Why not?
You can just look it up.
You have a textbook that has all of the facts in it. There's no point for me to exist. Okay? The reason I'm here is to provide some of that kind of background context and the explanations for why and how we're getting to those factually correct things. Okay? So in this case, if we do, after our big reveal, we're missing some information. Okay? That information is embedded in that footnote. Okay? And even then, arguably the information isn't, the factualness of it is provided there, but is there an explanation for it? No. Okay? So what we could do as scientists was go, this is what I would predict it to be, test it, oh, I'm wrong, why am I wrong? This would be part of that failure aspect and going back and trying to reevaluate it. The why behind it is really, really hard and outside the scope of the class. So we don't need to stress about the why here. We just need to acknowledge what was our theory behind this. Yes, that theory failed. That's okay. We would need to adjust our theory. Make sense? So it's kind of a good thing and a bad thing. It's a good thing because you don't have to be right, but it's a bad thing you have to explain why you're getting the wrong answer. Okay? And that explanation is usually the harder part. Okay? So, predicting chemical properties. Our periodic table has some organization. What was the name of a vertical column? And don't tell me vertical column. A group or a family. And that's because within that family, they all react similarly. So if I look at the alkali metals, when the alkali metals react with oxygen, they always have the general form M for metal. Because if I'm looking at the alkali metals, all of the elements within it would be M, okay, or a metal. There's two metals for one oxygen. So if I look at the oxide for lithium oxide, there's two lithiums, one oxygen. Two potassiums, one oxygen. Two cesiums, one oxygen. Kind of makes sense? Okay. This little activity is if we had a little bit more time, so we won't stress about the activity, but we will kind of look at a potential way that this can get asked on an exam. So usually a lot of the suggestions that students will come up with for exam questions are inherently obvious answers. Okay? So you could just do pattern recognition to come up with your answer choices. So one suggestion that usually comes out is, given all of those, what's the formula for a sodium oxide? Na2O, right? We would just say the answer is Na2O. Okay, well, if it's a multiple choice test, I have to provide 4 wrong answers. So I could do NaO2. I could do Na2O3, right? These are some other wrong answers. Would anybody guess those answers given this information?
Probably.
Why not?
Because they all match together.
Yeah. None of those formulas match these formulas for wrong answers. Okay? So while that kind of gets at the concept, it's a horrible multiple choice question. The design isn't there. Okay? So we want to come up with a given information that allows us to say some of those wrong answers could be valid. So here's the design. If we go for our sodium oxide again, whoops. And let's drop in. Given lithium oxide's formula, aluminum oxide's formula, silicon oxide's formula, and magnesium oxide's formula. What is the formula for sodium? Okay. Well, NaO2, hey, that's matching the formula for the silicon. The Na2O3, that's matching the formula for the aluminum. Okay. Now those answer choices become much harder to discern, and you have to have a key piece of information. What is that key piece of information? Within a family or a group, they all react the same. Where's aluminum with respect to sodium?
On the other side. So
In the period, not the group. Okay, where's magnesium? Immediately next to it. Oh, it's closer to it, so it must be more similar to it. Not within a period. Okay, does that make sense? So the design of the question has to be such that your multiple choice answers are all potentially valid answers. Okay? That makes it a much more challenging question for you, and you have to know the content. What is the content? Members of a family have similar chemical properties. Well, what the heck's a family? The vertical column. So if I'm being asked about sodium, I would find sodium on my periodic table. Using my given information, I would see which of those metals is in that same family. Now I have an answer choice. You had a question, Kara?
Is it actually like that for most families?
Yes. Okay. And for largely where we keep our focus, that chemistry holds true for virtually everything we do. And we look at these first two columns, which are pretty much spot on perfect, and then boron through helium or boron through neon. Those are all pretty much spot on perfect. Right? Everything within that family reacts similarly. Of course, we run into a slight issue with the far side, right? Why?
They're noble gases and they don't react.
Phosphorus is non-metal. Bismuth is arguably we could go semi-metal or metal. I was hoping to hit metal. Okay? The property has changed because we've got that diagonal there. Metals versus non-metals. Okay? Even still, their electronic structures are similar enough that they react very, very similarly.
Does
Okay.
that also include the two columns at the bottom?
There are two sections, arguably, of the periodic table that I have not pointed out yet. Number one, the two series or rows I did not point to, and then I also did not reference the column scandium to zinc. Okay, why not? That trend of electronic properties or chemical reactivities is mostly true, but there are some kind of wild exceptions. Okay? And we will hopefully talk about today potentially why we would start to see exceptions when we hit those areas of the periodic table. Okay? So, periodic trends. This is kind of a fun one. So, what do we measure when we talk about size? When I ask for the size of an atom, what am I talking about? Okay, that's a hard one. If I asked you to describe my size, okay, someone came up to you and said, I heard you have that teacher Mike. What's his size? I don't know. They're being really picky, but you know.
You want exactly?
How would you describe my size to that person that has never seen me before? Tall. Is that it?
Skinny.
What are you saying by skinny? And I'm not trying to be like accusatory because I know that's what that looks like. What are you implying by using the word skinny?
figure.
What did you suggest?
Weight.
Oh, weight. So when we think about size, we're really referencing two things. We're referencing height, how tall I am, which really has nothing to do with my weight, and a combination of weight. So there's really kind of two features that we could address when we talk about size. That is not the case in chemistry. When we talk about size in chemistry, we are very specifically referring to
Weight.
the height-ish of the atom. So really how large around it is. Okay? And why might I differentiate that? For an individual person, when you're talking about my size, my weight is roughly evenly distributed across my whole body. Is that true for an atom? No. Okay, so since we got a no, she doesn't have to explain. Everybody else gets to explain. Why is the weight not evenly distributed across the entire atom? So we got a suggestion that it's all within the nucleus. Shh, you already jumped, and you already jumped. So keep refining. What is it? Protons and neutrons. Why are you not talking about the electrons? The electrons don't have mass. So when we talked about knowing the properties of those individual subatomic particles, this is where it matters. Okay? When we think about the size of an atom, we aren't referencing its weight, we're talking about the superdome. Okay? When we talk about the mass of an atom, we're saying the entire superdome mass is balled up into the nucleus, a marble within it. The rest of it is pretty much open space. Okay? So when we're talking about size here, what are we referencing then? We're talking about the big around. Okay? So what particle contributes to the big around? The electrons. The protons and neutrons are located centrally in the nucleus. They aren't contributing to the size, the outer part. The only thing contributing to the size outer part is the electrons. Okay? So we've got our electrons being our responsibility for size. So let's go ahead and pick hydrogen versus francium. Okay, so hydrogen H, francium Fr. Which one do you think is bigger? Why? Francium has more electrons. How many more electrons? 86. At this stage, all we're doing is talking about neutral atoms, so the balance of electrons and protons is the same. So when I talk about a hydrogen atom, it has 1 electron. When I talk about a francium atom, it has 87. So there's 86 more electrons for francium than there are for hydrogen. Since electrons dictate size, more electrons probably means bigger. Everybody okay with that? You're like, yeah, that kind of makes sense. Yeah, I agree. I think that kind of makes sense. Where did we look? Through a family. Okay? Was there another direction we could have moved on the periodic table? Yeah, we could have moved on the horizontal or through a period. Sure, I was using the wrong word in my head. Lithium versus neon. Okay, what happens to the number of electrons? How many electrons does lithium have? 3. And the number of electrons neon has? 10. Which one would you predict to be larger? Neon, because more electrons. Cool, right? When we go down a group, the size gets bigger. That's what this says. Awesome, fantastic, we love that. Be careful writing. When we go left to right, across a period, it gets smaller. So let's run through that again. When we go left to right, so my left is lithium to neon, left to right, the trend gets smaller. What did we just say? It sure got bigger. What does that mean? We're wrong. Okay? What else changes as we go left to right? Is it just the number of electrons? Fair point. I got no way to work with that, though. So metal to non-metal is a fair point to note that it's changing, but I can't use that. Because this trend will still work lithium to beryllium, and we would get the same change there. So what else is changing as I go from lithium to neon? The amount of protons. So if I have more protons, I'm making a larger, stronger positive charge. what might we expect to happen to the electrons if I have a more positive charge?
To draw in.
They should get drawn in. Okay, your positive and negatives are opposites, kind of like magnets, north and south ends of a magnet. If I have a stronger north end, what is that going to do to the same south end?
Draw it in.
It's going to draw it in a little bit tighter. Okay, so cool. That must be what's going on then when we look left to right. We have more protons, so that's why it's getting smaller. Okay? And the careful, critical mind will then ask, why doesn't that happen down a column? Because down a column, what's also changing? The number of protons, and yet what's happening to the size? It's getting bigger. So we've now come up with two potential explanations for these changes that we're seeing in the radii. However, when we come up with one definition, the other trend doesn't make sense. Okay? When we use a different definition, the other trend doesn't make sense. So something is fundamentally flawed about how we are looking at our atom. Okay? And in particular, we can tie this back to the whole argument. What particle is evaluating size?
Electrons.
The electrons. Have we had a discussion yet about where our electrons exist? Just outside the nucleus. Okay? So what does that mean about our theory about where our electrons exist? There's something wrong about it. The electrons can't just exist anywhere outside the nucleus. There's something inherently missing about that explanation. Okay? That's now being manifested and observing those trends. Okay, we will come back to evaluating these trends. Ultimately, you are responsible for these trends, so you do need to memorize them. These trends are absolutely true, okay, for the most part, okay, at least for the most part where you get tested. So you can memorize those trends. Okay? There's other ways that we can look at it. So we can look at nice fun pictures. Down a column, if we look consistently, down the columns, what happens to the size? They all get bigger. Across a row, okay, particularly when we get over to this side of it, like aluminum to chlorine or boron to fluorine, we might say, well, I can't really see a difference. Okay, that is an important observation that becomes super relevant in organic chemistry. Okay? In organic chemistry, though, these numbers, we're like, what the hell is that? I can't deal with numbers. I just look at these pretty pictures, and those look about the same to me. Because you're in general chemistry, you have to worry about numbers. When you look at the numbers, what happened to the numbers? They did indeed get smaller. Okay? Oh, interesting, yeah. We don't get an exact trend across. Okay? Remember how I said there were two groups for the families that I was like, we're going to kind of ignore these? Which two groups was I talking about?
From zinc to...
Our zinc to our scandium and these guys. Where are those two groups found? So you could say right in the middle, left to right. I'm going to argue there's another thing that's more important left to right. Or not necessarily left to right.
Up and down.
Up and down. Okay? Those elements are located lower on the periodic table. What happens when we get lower on the periodic table? More protons, more electrons. The more things we add, the more complicated it becomes. Most of what we do, we keep at the top end. Why? Because we're starting chemistry. We're trying to get the basics down. Once we get the basics, we can worry about making it more complicated. So you're right in noticing there's a weird trend happening down here that doesn't match. Where's that weird match? At the bottom of our periodic table. So we are starting to see some weird things happen here. So those are trends, not exact rules. Okay? So one of the things that you could start to do is when you see a periodic table, draw out some kind of arrows on it. We will be talking about this when it comes to the exam. You should be doing this when you get the exam. You've got a periodic table printed out with the exam. You should be drawing arrows on it almost instantly as soon as you get the exam. Why? You now have a map of your answers. If you wait to find the question, that maps those answers, what do you run the risk of doing? Potentially running out of time. I would argue a larger issue, forgetting the trend. And because each of the questions is going to show different ways to apply those things, you could very easily confuse yourself with the wrong answers. If you write down the trend right away, the odds that you're right in the first 5 minutes are probably pretty good. The odds that you're right in the last 5 minutes of the test, probably not so good. Okay? So if there's things that you want to hold on to for the test, to have memorized that you think are super important, you should write those things down immediately when you get the test. That way you don't have to hold on to that knowledge anymore, you just have to go back and find where you wrote it. Make sense? Okay, so back to chapter 4. So we did a little bit in chapter 4, then we did a little bit in chapter 5, now we're going back to chapter 4. Okay, the first part of chapter 4 talked about our protons and electrons, or protons and neutrons. Okay, first part of chapter 5 was talking about the organization of the periodic table that was largely based off of the nuclear charge. You mean the protons? Yes. Okay. The second half of chapter 4 now talks about electrons. Second half of chapter 5 talks about electrons. Okay? But in a slightly different context. So, to start it off with, electrons are nasty little buggers. Okay? We said ultimately their mass was effectively 0, but they are still something, so they weigh something. So we're saying we have a particle that has mass, but we're going to say it's 0 mass. Okay? Does that sound a little weird? Yeah, that's kind of contradictory. Okay? When we talk about matter, matter can move in a couple different directions. We've got matter that is like a particle. When I throw a ball, it moves in a very regular fashion. Does light do the same thing? If I turn on a light, does the light move in that single direction? No, it moves as a wave. So we get two types of descriptions for how matter can move, okay, or our observables can move. We get this wave and we get a particle aspect, okay, that aren't the same. Guess what electrons have? They have mass and no mass. They also move like particles and like waves. So there's this giant, confusing, just ball of everything that's contradictory. We put it into a single particle and said, ta-da, electrons. Okay? So when we think about electrons, we have to be a little bit careful. And one of those things that we need to be aware of is they have a wave nature to them. Okay? So that wave nature is now what's discussed in chapter 4, the basics of waves. You get wavelength and frequency. Wavelength is the distance between two peaks. First and second peak. Frequency is the number of peaks that show up within a given distance. Okay? So these things are related to each other, but not the same. Okay? For instance, if I look at this thing with a high frequency, what happens to its wavelength? It gets really, really, really small. Okay? That peak-to-peak distance is small. If I look at something with a low frequency, what happens to the wavelength? It gets really, really, really large. Okay? So what I want you to do is be aware of those concepts. You don't have to mathematically do anything with them. There's a number up there, 3 times 10 to the 8 meters per second. That's neat. That's the speed of light. Cool. Exciting. Don't worry about it. There's a formula. E equals H weird V thing. What is the weird V thing? Close. Frequency. The other F word. Okay? It's our frequency. Thank you for whoever kind of exasperated over there. Frequency. All right, what is H? A random constant that allows us to correlate frequency to E. What is E? Energy. Okay? So light has energy associated with it. Okay? That's all I want you to get out of that. You don't need to calculate it, just light has energy. Ta-da! Light is also made up of wavelengths and frequencies. Ta-da! Lovely. Okay? Now, where is light? Light is part of the electromagnetic spectrum that ranges from cosmic rays all the way down to radio waves. Okay? In that, we have visible light, which ranges from our violet light to our red light. What colors are in the visible spectrum?
Oh, do you want me to say it again? Roy G. Biv?
Roy G. Biv. That doesn't sound like a color to me. What do you mean?
Red, orange, yellow, blue.
Red, orange, yellow, green, blue, indigo, violet. Okay, so our Roy G. Biv. That's a nice little way to memorize our spectrum. That's a Y in between. Didn't get much better.
It looks like you tried to fix it and then it
V,
just like got out of hand.
I, V, Roy G. Biv. So now we know the visible light spectrum. Okay? Which is the highest energy?
Red. Violet.
Ah, so we're all over the spectrum on this. Okay, so let's try this. Ignore the rainbow for the moment. Which of our electromagnetic spectrum is the highest energy? Cosmic gamma rays or TV radio?
The cosmic rays.
Cosmic rays. How could I remember this? Because we all, of course, see all the Marvel superhero movies. How did the Hulk come into existence? Gamma rays. So he becomes strong because he absorbed high energy particles. If he had just absorbed radio waves, nothing was going to happen. Okay? So it's those high energy gamma rays that cause the Hulk to be super big, beef, strong guy. Cool. Okay, but that means I'd have to memorize all of those individual wave or areas of the electromagnetic spectrum. I don't want you to do that. All I want you to do is know this rainbow, the visible light spectrum, and be able to tell me the energies. Okay? Well, gamma rays you said was the highest energy, so purple's closest to gamma, which means the purple must be
Or violet.
the higher energy. Okay, but that requires that you know purple was closer to gamma. Well, because purple begins with P and gamma begins with G, it's obvious. Okay, hopefully you're laughing because you're like, that's stupid, that's not obvious at all. I completely agree. Okay, that isn't obvious. Okay, and you could say, well, I can see it on this spectrum. Except on a test, what spectrum are you looking at? You aren't looking at one. All you've really got is probably Roy G. Biv. So how could you remember which of those is higher in energy? You could just blanket memorize it. The way I like to think about it is I step outside into the Arizona summer, and what am I concerned about? Concerned about what? Sun exposure and ultimately ultraviolet light. Yes, heat is a contributor, but when we go outside into the sun, we aren't slapping things on to protect ourselves from the heat. We're slapping on like sunscreen to protect ourselves from ultraviolet light, UV radiation. Why would we protect ourselves from the ultraviolet radiation?
Give you cancer.
Why does it give you cancer? It is high in energy. Which of my colors, violet or red, is closer to ultraviolet?
Violet.
Because I know UV radiation is high in energy, I now know that my violet light is higher in energy than my red one.
You can also remember red radio. Because you said that it was on the other end of the spectrum, it's the radio.
Oh, red radio. Okay, sorry. I heard radial, and I was like, what do bones have to do with any of this? Okay, red radio you could work with, assuming you knew radio were lower in energy. There was another one that was immediately next to red. What was that one?
TV.
Where's my thing? There's the red. Oh my gosh. Which came in. Da, 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 da. There's our visible, right? What's that one that immediately came in next to red? Infrared. How many of you are concerned about infrared radiation? Should we? Good point. You were already concerned about ultraviolet. Why aren't you concerned about infrared?
I'm not expecting night vision goggles to be on my body.
Why aren't you concerned about infrared?
Slow energy.
It's lower in energy. That's why I don't have to worry about it. So you can remember ultraviolet being high, violet's closer to ultraviolet, or you can remember the very next thing after red is infrared, which, damn. That was damn as an acknowledgement of that was a good thought. We're going to come back to that in a second. Okay. Low energy. Okay. Which of our colors is closer to infrared? Red, which means red must be the low energy one. Okay. The other part with this, which was just suggested, which didn't make it into the recording, which is pretty cool, that's the damn statement here. Infra, we could start going inferior. It's inferior because it's lower in energy. Okay? That's what I want you to do with those light spectrums. Make sense? Cool. So, what are we doing with this light? Because light plays an integral part in how we understand our electrons. Remember the whole wave thing? Turns out those wave things in light give us direct evidence for where our electrons exist. Okay? If our atom, nucleus, and our electrons can exist anywhere in here, right? Anywhere at once. Okay? So that's our that was our working hypothesis to begin with. Okay, so what somebody went through and did when we created that vacuum, well, let's start doing things with it. Let's take that vacuum and I'm going to put a small amount of just hydrogen into it. What happens? I have a glass tube with hydrogen in it. That's what happens. That was it. That's literally it. I just have a glass tube with hydrogen in it. That's kind of boring. I don't see it. Hydrogen's gas. Whoop-de-doo. I'm going to take that same glass tube with just hydrogen in it, and because I think it's kind of funny when we do like the handshake with the little electronic buzzers, right? Have you heard about those? You got the little buzzer on your hand and go, hi, nice to meet you. Zzz. Yeah, it's kind of hysterical, right? Okay? And what's extra entertaining about that is that that creates kind of a buzz that kind of freaks people out. So I'm going to do the same thing and see what happens when that buzz hits an element. So I'm going to take that glass tube, and instead of it just being hydrogen, I'm going to attach some electrodes on the end of it, kind of like a cattle prod. Okay? And I'm going to pump a bunch of voltage through it, a bunch of electric current. And we're going to see what happens to that whole process. Well, I'm pumping electric current in, which means what's the most likely thing to move? Electric current. What's the most likely thing to move? What's in the tube? Hydrogen, which is made up of electrons. When I'm pumping that electric current in, the most likely thing to move will be electrons. And what would that electron do? Okay, well, what would you do? So, because no one was here earlier, I could put a little buzzer under one of the seats, and with this little remote access button, we could see what would happen if we would do this. So we're ready to see what would happen.
Probably move.
So good, we at least got one person to respond. Okay, what are you freaking out about? What are you freaking out about? Because this is just a microphone. What are you freaking out about? Getting shocked. Because what's going to happen if you got shocked? Number one, a lawsuit. Number two, what's going to happen to you? What are you going to do? You're going to jump. What's the electron going to do? It's going to jump. Okay? What do you do, assuming we ignore all the lawsuit fun stuff? Yeah. What do you eventually do, assuming you aren't entirely irritated at me? Laugh. And then what? Sit back down. What happened to that energy that jumped and caused you to jump up? It didn't just disappear. Where did it go? Right? If I made all of you jump up and down a whole bunch of times in here, what's going to happen to the room? It's going to get hot. Where did the energy go? Into heat. Electrons do something a little bit interesting. They absorb that energy and they make that jump and they go, I'm going to relax back down. When they relax back down, what do? What do? It's not like we just talked about parts of the electromagnetic spectrum that involved like they release light. okay, which is a form of energy. If our electrons can exist anywhere in there, okay, when they relax back down, okay, for number one, when it jumps, it could jump to any one of those positions, anywhere in that thing, which then also means it could relax to any one of those positions, which means how much light would I expect to get out of this?
Not a whole lot.
I can jump at any energy level. If I can jump to any energy level, which color light corresponds to any energy level?
Green?
The violet, if you go up,
So violet, what energy corresponds to violet? High. Is red high energy? No. So when you say any energy and you tell me violet or you tell me blue-green, you've picked an energy. If the model of our atom is correct, where the electrons can exist anywhere, what color light do I get? All of them. Okay? So what I would see from that should be white light. I don't see white light. Okay, so maybe they can only jump, kind of within certain ranges. And if it's kind of certain ranges, I won't get white light, but I might get a little bit of color where I see a whole bunch of purple, a whole bunch of blue-green, and in this case, let's say a whole bunch of red. Okay, so I see still a spectrum within those ranges. I don't even see a spectrum. What I see is a line. I see a single value, a single energy. What does that mean the electron's doing? It can't just be chilling, because it had to jump, and when it came back down, it released that energy. What are the jumps that it's jumping on?
like a wavelength.
By saying a highest and a lowest energy, you are now defining points at which it can jump. What we're looking at now is a staircase instead of a ramp. On the ramp, we could exist at any point on the ramp. When you came up the stairs this morning, could you exist at a step and a half? If you took that step and a half and expected there to be a step there, what happens?
You fall.
You fall until your foot hits that next step up. Okay? And then maybe you fall and hit your face. Hopefully that didn't happen. Okay? What if you only took 0.9 of a step?
You probably trip.
You trip, you don't make it up the stairs. You're still on the first step. The same thing's happening with our electrons. Our electrons can only exist at particular locations around the nucleus. The electron can exist here, here, or here. Okay? When the electron starts, it's going to start at the lowest energy. Why would it start at the lowest energy?
Because there's not much giving it energy.
Where are you guys starting this whole class?
In the beginning.
Where are you personally starting the whole class?
At different levels.
Time is irrelevant. What's your level? What is that?
Sitting.
You're sitting. How many of you are standing during this class? Oh, none of you. Why not?
Because it takes more energy.
Standing requires more energy. You are naturally going to the lowest energy state. Guess what chemistry is doing? The exact same thing. It's going to go to the lowest energy state. I pump in the cattle prod, 20,000 volts. What's it do? It's going to jump. Okay? Now what's it do? If I told you to all stand, what are you eventually going to do? Sit back down. Why? You want to go to the lowest energy. So that electron got jumped by the cattle prod, and then eventually it goes back down. Where did the energy go that it absorbed? Where did your energy go? Heat. Where does the energy for the electron go? Into light. That jump corresponds to that single light. Because I have atomic line spectra, I now have direct evidence of where electrons exist. They exist not just around the atom or around the nucleus. They exist at particular locations around the nucleus. And they cannot exist in between those locations. Okay? In past chemistry courses, you may have heard these referred to as orbits. And in fact, our textbook refers to them as orbits. Okay? The initial descriptions of this may have called them orbits. It is horrible to call them orbits, because when you think orbit, you think like the moon moving around Earth. That's not how it works. Okay, these are orbitals. Our approximation is that they exist in orbits. Okay? So if we look at this, here's our electron. Ta-da! 20,000 volts, it jumps. Okay, what if I gave it 15,000 volts?
Lower.
Why are you saying lower? Because everybody else said higher.
Well, lower as compared to the 20,000, so it won't go into.
Where's the lower step than 20,000 volts?
The other
There isn't one.
There isn't one. If I give it 15,000 volts, what does the electron do?
It settles in between the two.
Can it exist in between? If I give it 15,000 volts, what does it do? Trips, falls on its face. It doesn't move. This is you taking 0.9 of a step on the stairs. You can't make it. What if I give it 40,000 volts? Now it could jump further out. Okay? So 40,000 volts says maybe it gets out here. Don't stress about the quantification. These are examples. If I'm at that 20,000 volt line, eventually, what do?
Go back down.
I come back down. That's going to release light, which we typically represent as h nu. Okay? And actually, bear with me for a second here. Let's do a little bit of color coding. H nu comes back down, and it releases h nu. H nu. G-N-U, the Greek letter for that squiggly thing, because it's a Greek letter. Okay? Which of those two lights would I expect to be more red? Why 20,000? It's a smaller jump in energy, which means lower in energy, which means I would expect the red light. Why would I expect the red light? Red is lower in energy than violet. Okay, so look at that, I even color coded it. The bigger jump got a blue color, because that's higher in energy than the red one. Okay, what if I had jumped with 60,000 volts? Somewhere out here, 60,000 volts. When I come back down, what is that going to be? And actually, let's switch this up. Let's not even make sure that isn't blue. We'll call that violet. That jump at 40,000 was violet. What color light do I expect for 60,000?
cosmic. Violet.
Why did you suggest cosmic?
Because cosmic was off the radar and
Violet was our maximum visible light. If I'm going to make a bigger energy jump, it can still happen, but am I going to see it? No, that energy jump is now outside human detection patterns and we don't notice it. It's still there, we just don't see it. Same thing could happen on the inside. Okay? I could do a smaller jump than that red one and not see it. Okay? Bohr is the one that came up with this theory. Okay? So we give Bohr some credit for this, for acknowledging that because we have atomic line spectrum, we have distinct orbitals where the electrons can exist. Right? That's why we get atomic line spectrum. Yes?
is there a way to see those, like the cosmic or like?
We have ways to detect those other things. We just wouldn't see it in an atomic line spectrum because the whole point of the atomic line spectrum is to be visible.
For the
Okay? So that the human eye could detect it. Okay? What we're referencing here is what's known as the quantum concept. Okay? Quantum or quantized, meaning defined values. The other term you could get is discrete. When you go up the stairs, there's discrete energies. You can't exist at a step and a half. You can't exist at 0.8. You have to be at 1 step, 2 step, 3 step, 4 step. Okay? A ramp, on the other hand, it looked like Laura got that one. Okay? A ramp, on the other hand, I can exist at all of those steps. That's a continuous spectrum. So when we're talking about quantized, it's usually best to reference it in two cases. We get quantized and we get continuous. Our initial model, which is why we got the atomic radius wrong before, was that we said it was a continuous place for the electrons. It's not continuous, it's quantized or discrete, okay? Which Bohr defines. Make sense? Okay, so if we actually look at this atomic line spectrum, it turns out that when we look at our electrons, we put hydrogen, because this is the atomic line spectrum from hydrogen, we put 20,000 volts in it, and the color lights we see show from these corresponding orbits. The purple light is from 5 to 2. The blue-green is from 4 to 2. The red is from 3 to 2. But I thought the electron would exist at step 1. Why are they jumping to only 2?
Is it not enough pull from proton?
They are. But the jump from 3 to 1 is such a large energy range that where is it going? In the ultraviolet spectrum. I can't see it. Those jumps are also happening. They just fall outside the visible range. It happens for hydrogen. The jumps that we're seeing are going from our higher orders to the second energy level. That's where we're seeing that visible jump. The exact value behind those jumps isn't super important. It's just acknowledging those distances change, and as they change, we'll see different visible lights, or they fall outside of our visible range. Kind of makes sense? Okay. A way to think about it, you all started at your ground state. Joey decided he was tired of sitting. Phenomenal. Thank you for that, by the way. Okay. For this analogy, he decided to stand up. Is he just freestanding in the middle of the room? No, why not? It could be in people's way. Is that why you're going back there? Yeah? Are you leaning against the wall? Leaning against the wall.
Because it takes too much energy to stand up in a free state.
Standing up in a free state is too much energy. So what does he do? He decides he doesn't want to sit. He needs to move around a little bit, so he leans against the wall because that takes a little bit less energy. He's dropping to stage 2 instead of dropping all the way down to sitting. Okay? Each of those stages are intermediate levels of energy. You can fully stand if you want now. Sorry. Okay? That's what's happening within those. It just happens that whichever ones we see are the ones that show up in our visible light spectrum. Kind of make sense? When I move from hydrogen to helium, what changes? Protons. Is that it?
Electrons.
And the electrons. If I change the protons and the electrons, what happens to the energy of each of those orbitals?
It's higher.
They get farther.
Easier than that. You guys are trying to get too specific, which is awesome. Get less specific. They change. If they change, what happens to each of those jumps or visible light jumps? Less specific.
They become brighter because of warmer.
They change. That's it. If they change, what does that mean? I see a different atomic line spectrum. Which means when I take an element and pump 20,000 volts through it, it's going to generate a different atomic line spectrum. Which means I can use the atomic line spectrum to identify the elements that are present. It becomes a fingerprint. Okay, so you might hear them referred to as fingerprints because they're characteristic for that element. Okay, oh, who cares? Anybody looked at the stars? Yeah, some people do it professionally and aim a telescope at the stars. And you can put different filters in it to pick up different wavelengths of light and all that kind of fun stuff. Okay? Those filters can be used to break down the color light that's coming in and hitting the telescope into atomic line spectrum. But it's going to be the atomic line spectrum for every element that is generating that light. So when an astronomer looks through their telescope and looks at the atomic line spectrum, it could be a combination of all of these. What could they do? They could break those pieces apart to find out the exact elemental composition of whatever they've got the telescope aimed at. What? Yeah, that's pretty cool. So they're talking about, oh, we know the sun is this much hydrogen, this much helium. That's what they did. They aim a telescope at it, they break down the atomic line spectrum of it, and they say these would be the compositions, this factors in. They can figure out the percentage based off of what you were suggesting, the amount or the intensity of the light coming through. Okay? That's pretty cool. That's our atomic line spectrum. Okay? And I don't know anything else about that, so we'll just have to stop there. Electron homes. So what we've now defined is that we have electrons and they exist in these discrete energies. Okay? For the sake of this drawing, the nucleus is somewhere down underneath the projector. Way down here. So this is my first energy level. Because I'm a creative person, I want to name the first energy level. Give me a name. 1. And everybody going, damn, she's not creative. She is just as creative as every other scientist out there, because guess what they named it? 1. Okay? The next one.
2.
The next one.
James, you're up.
3. Amazing. Okay? And they went through and they named these according to those numbers. Okay? Anybody see how that could potentially get confusing? We're using a numeric system, which we're used to doing mathematics with, addition, subtraction, multiplication, and now it's being used as a naming system.
Oh God.
So in algebra, you can go use alphanumeric or alphabet letters to represent variables. Frickin' chemists are doing the other direction. We're using numbers to represent the names of things, not numerical values. Writing systems. Just checking. Okay? So, anybody knows anything interesting about these other than they're drawn horribly? So let's make them look better.
They're too close together once you get closer to the top.
As we move further and up, the distance between the energy levels gets smaller and smaller and smaller. The maximum value, because there is a maximum, is the vacuum. The electron is now such a high energy that it is not associated with the atom anymore. Okay? So on this, what we have implied is two things. Energy goes up, and distance goes up. The further we are up this diagram, the further away the electron is from the nucleus down here. Okay? So this diagram has two pieces of embedded information, energy and distance. Why would they be tied to each other? The shorter the distance is, what happens to that electron? I have a short distance between the electron and the nucleus. Not a bad idea on trying to relate that, but believe it or not, simpler. What's in the nucleus? Protons. What happens when I get a negative near a positive? They attract. Why are they attracting? Because they're trying to cancel the charge. The further from that positive I get, how much is that charge canceled? Not as much, which is why it's higher in energy. Okay? So, we've got our energy levels. If we tried to now dump electrons, we're done at 45, right? Okay, just checking. We've got our energy levels. We can now start dumping electrons in. Where would I predict the first electron to go? The first level. Why did you pick the first level? It's the lowest energy. When you all came in, you sat in the chairs. You didn't just stand there and stare at us. Okay, we go to the lowest energy. Where's the next electron going to go? Why should it go to the second energy level and not say to the first? Somebody else is already there. Electrons are negative. If I put two negatives near each other, they repel. So I would predict this to happen. Okay? When it comes to our energy levels, how many lines do you see here? 1, 2, 3, 4, 5, 6, 7. And the 8th one is our vacuum. So let's just say vac. Okay, so that's actually not an energy level. That's now outside the realm of the atom. So how many energy levels are there? 7. Okay, remember, periodic table, those bottom two rows are just confusing, so let's just ignore them. Why 7?
7 seems to be like the triad pattern.
Because there's,
For two of the periods.
there's.
Why 7?
Sorry.
There's 7 families, or there's 7 periods. Or series.
There are 7
Period.
periods or series. How many energy levels are there? 7. How many periods are there? 7. That seems awfully kind of coincidental. It's not coincidental. It's intentional. Okay? We are organizing the periodic table to acknowledge the fact that we have those 7 energy levels. What's going on with those bottom two? Wouldn't that be 8 and 9?
No, because they're.
8 and 9 are actually here. They're embedded inside the periodic table. Okay? To get at rhetorical choices for visual design, why did we not take those and drop those in the periodic table? What would happen to our periodic table? Yes?
It makes it too like long.
It makes it really, 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 really long.
We need 8.5 by 14.
Okay.
instead of 8.5 by 11.
If it's really, really long, that makes it now
Harder to understand. And
harder to understand. Okay? So we are making an intentional choice to pull that information out to make it a little bit easier to process. Okay? That would be, I have it in my notes. Literally wrote it in my notes in the other class. Is that structural? Structural element for visual design? Because we're changing the structure of our periodic table so we can better understand the pieces within it.
Blend of structural and technological, yeah.
Damn it, technological is the other
So
one I was going to say.
structural, yes, absolutely, but because you're changing the structure so that it's easier to take up information, then that's technological.
Okay. Does that kind of make sense? So those 8 aspects are tying back to how we build the periodic table. Yes?
So does this go back to the whole atomic, like, radius as it increases and decreases?
It will. We aren't there yet. So if we have 7 energy levels, how many electrons can I fit? 7. How many electrons according to my periodic table?
7.
Try again. How many electrons?
118.
118. 7 does not equal 118. What does that mean about my theory? It's wrong. Good call. Turns out the second electron goes where?
The first one.
The first one. But don't electrons repel? Yes. But it turns out, this is a weird kind of quantum thing, so you don't have to stress a whole lot about it. Our electrons spin.
What?
Yeah, they spin. Okay? You can spin clockwise or counterclockwise. If you spin clockwise, you don't want to see another one spinning clockwise. You know, everything's all mismatched and that's confusing. But if there's one spinning counterclockwise, you're like, okay, you can hang out with me. Which means, how many electrons can I fit in an orbital? 2. As long as the spins align differently. So sometimes you'll see arrows attached to your electrons to represent that. Okay? Now how many electrons can I fit? 14, which is also not 118. I'm better, but I'm not there.
Doesn't it, as it gets like, as they start, so the first one's like the smallest, but as they start going, they get bigger.
As our energy levels increase, we're starting to get further away from the atom, which means we can actually cram in more orbitals. So starting with our first energy level, we get 1 orbital that looks like a sphere. When I move up to the second energy level, that second energy level will copy what it had before. Okay, just like what you guys are doing. You are copying past work so that you can then build on it and make more. Okay, so there we go. Copy. And I need a new one. There's my new one. So that second energy level splits out into 2 different orbitals. Okay? The third energy level will then split out into 3. The fourth? 4. Each time we copy the previous one's work. You'll notice that as we move further on up, the shapes get weirder and weirder. Okay? I drew that one horribly, but the textbook's gotten better, so look at the textbook. Okay? So I could then go through and add in more electrons. If you propagate that all the way out, it still doesn't quite work. Right? So there's another layer on top of this. Not only do we have energy levels that can hold 2 electrons because of spin, we have orbital types And then we also run into orbital orientations. Okay? So this bottom one, drawn as a circle, but remember this is a three-dimensional object, which means it's not really a circle, it's a sphere. Okay, so if I just had a ball here in my hand, okay, and we all looked at it, then I asked you to close your eyes, and then I did something, and I held on to the ball again, and told you to open your eyes, would you be able to tell me that I rotated the ball? No. Okay? All orientations are entirely equal, which means there's only one possible orientation for that sphere shape. Okay? What about if I move up to the second energy level with that sphere? Would I be able to tell? It's still a sphere. I still can't tell. So yeah, I think you're looking at me like, you're an idiot. It's still a sphere, right? Yeah, it's still a sphere. You can't tell. But the dumbbell.
Yeah, because the.
Now if I turn it, you would be able to see that. Okay, so there are now orientations to this. The orientations for the dumbbell happen to fall on, whoops, let's pick a better color. What am I trying to represent? The three dimensions, y, x, and z axes, or the z's coming in and out of the plane at you. This is now our final state. Every time we move up, we copy the previous work. We add a new one. That new one gets more orientations. That's how we get to our final state. Okay? So now I want to be able to describe where any electron is located. Okay, so we're just going to deal with these. So 1, 2, 3. So you'll notice that we typically just use lines to represent these. Right? Okay, so my electron I'm now going to draw in red. Where's that electron?
Second energy level.
So it is in the second energy level.
The first orientation.
Okay, the first orientation of what? Of the sphere? So we said orientation, so we could actually say the y orientation. The y orientation of what? What is that? An orbital. Isn't this also an orbital? Yeah, so if you say the first orientation of the orbital, do I know which orbital you're talking about? No. Fix it. Is that one kind of hard? Maybe let's back it off and let's try something else. So a new electron, we'll call it a purple electron. I'm going to put it here. Tell me where that electron is. Lowest energy doesn't count. Throwing that one out. Where's that electron located? First energy level. Okay. I don't know anything about chemistry. How many possible orbitals are there? There's a sphere. So that first electron is located in the first energy level and the sphere shape. Fantastic. Go back to our red one. Second energy level and the... Is it in the sphere? Okay. Y is the orientation. Okay. We might need a way to describe said shape. The shape that we use, in this case, yes, I said it very fast, but you all did the reading. Dumbbell. Do we really want to go through and use a word to describe each of those different shapes? No. You might be responsible for knowing what that word is, but if I'm going to come up with a notation to label these, I don't want to have to write those out. What might I come up with instead? A symbol. So instead of writing lithium, I could write Li. The X, Y, and Z are orientations, not a description of the shape. Okay? And it turns out the orientations we don't have to specify. Okay? So what kind of symbol do I want to use to represent sphere? Touché. When we looked at our elements, how many of our elements are pictographic? None of them. Do you think using a pictographic image here matches the context of our science thought? No. Okay. Why are you picking S? Because I think that's a pretty valid drop down.
As long as the other images are like the other.
What was the word?
Sphere.
Why did you pick S? Sphere begins with S. Awesome. What should we use?
D.
D. That's a phenomenal guess, except in German, dumbbell begins with P. The D orbital is this guy, the cloverleaf up above. Okay? So this shape is known as a cloverleaf typically, and is known as the D orbital. Okay? What we now have is the fundamental basis to describe atomic electron existence. We have an address for every single electron. So when we're thinking about atomic notation, it's your address. That's what you're working with. Okay? You now have kind of the rough context to be able to start to answer the Lewis structure video. Okay? So start watching that. The big two key words that are going to come out of that, valence electrons, are going to be super important. What we just described were all of the electrons. If I'm going to take two atoms and have them interact with each other, which electrons do you think I'm going to be most concerned about? The outermost or the innermost? The outermost. When you go up to introduce yourself, do you like bump hearts against each other? No, you shake hands because your hands are on the outside. Okay? And for those of you that are hugging people, I'm saying literally rip your heart out of your chest and like bump hearts, not doing chest bumps. It's an entirely different thing. Okay? Our valence electrons are our highest energy. So 1, 2, 3, 4. So when you look at an electron configuration, find the highest number in front, total all those electrons, that's your valence, that's what you need for Lewis. After that, believe it or not, you can do the Lewis structure videos.